This video lecture on calorimetry is meant to cover the information found in Unit 12, objectives numbers 2, 3, and 4, where we will identify, define, and convert the units used to measure heat transfer. We will apply the concept of specific heat in calorimetry calculations to determine energy, mass, or change in temperature quantities. And in the lab, we will use a simple calorimeter to determine energy lost or gained in changes in states of matter or in chemical reactions. So calorimetry is the study of energy changes that occur during chemical reactions or in changes of state of matter. Changes in states of matter are things like vaporization, freezing, melting, and condensation. Heat energy flows from a warmer object to a cooler object, and the unit that is used to measure heat energy is calories or joules. Calories is abbreviated CAL, and joules are abbreviated with a capital J. In this class, we will use calories. Conversions. Notice the difference in the calorie unit here. 1 food calorie with a capital C is equal to 1 kilocalorie, which is equal to 1,000 calories with a little c. So pay close attention when you go to write this unit. Big C versus little c is definitely different. 1 food calorie is what you would read on the nutrition labels, and this is used because otherwise they'd be putting fairly large numbers on the labels, and they're just abbreviated that way. So if you were to convert between calories with a little c and joules, 1 calorie is equal to 4.184 joules. So you'll be using those conversions a little bit later. We're going to take a closer look at exothermic versus endothermic processes. In an endothermic process, well, first of all, let's talk about the couple terminology here, terms to understand. When we talk about the system, okay, in this picture right here, the system is the ice cube. So if you could picture yourself as being part of the ice cube, right, and the surroundings being the table surface and the air, ice melting is endothermic because the system, the ice cube, is gaining heat energy from its surroundings. Okay, so the ice cube is gaining energy from the table and from the air, and so the ice cubes gain energy and the surroundings consequently cool down. So that's an endothermic process, endo meaning in. So energy is going in to the system. An exothermic process, if here we take a look at the system being the matchstick and the surroundings being the air, this is a chemical reaction that is exothermic. So this way the matchstick, the system is the matchstick, losing heat energy to its surroundings. So the system loses energy, but the surroundings heat up. So you have to be careful in perspective when you're thinking about exothermic versus endothermic processes. Now in the lab, we are going to be using what is called a soda can calorimeter. And it's a crude piece of lab equipment, to say the very least, but what you can see here is a soda can. What you can't see is that the soda can has water inside, and this is a thermometer that is recording the temperature of that water inside. Underneath is a food sample that is burning, and so as the food sample is burning, the heat being released by the food is being absorbed by the water inside the can, and we can measure the temperature change of that water, and we will use that temperature change to determine how much energy the water absorbs, and we will assume that the amount of energy that the water absorbs is equal to the amount of energy given off by the burning food. So a calorimeter is a lab technique lab equipment that is used to measure the energy content of food. First thing you would do is you would burn food. You would let that heat released be absorbed by some water in the soda can. and we measure the temperature change of that water. We must also take into account the mass of the water heated, and we must also take into account the specific heat of water. Specific heat of water is the capacity of water to absorb energy. The word energy is off your screen here. Specific heat capacities are unique to every substance, but it's defined as the amount of heat it takes to increase the temperature of 1 gram of a substance by 1 degree Celsius. So we can see here, these are quantities that are known and they're given to you. Liquid water has a specific heat of 1.0 calories per gram per degree Celsius. What that means is if you had 1 gram of water and you want to raise it 1 degree Celsius, it takes exactly 1 calorie to do that. Ice, here denoted by water with an S after it, has a specific heat of 0.51 calories for every gram to raise 1 degree Celsius. Gaseous water, a little bit different, 0.48 calories per gram degree Celsius. On the right side, you'll see specific heat capacities of different metals, aluminum, mercury, and gold. Notice the magnitude of these specific heat capacities are very small compared to water. Aluminum at 0.22, mercury at 0.033, and gold at 0.031. These are all given. These are not numbers you will have to memorize. But questions to ponder as you look at those specific heat capacities. Does it take more energy to heat up liquid water or to heat up ice? Going back to those numbers, does it take more energy to heat up liquid water or to heat up ice? And it takes more energy, you can see here the number is actually bigger, it takes more energy to heat up water than it does to heat up ice. Another question to ponder is, does it take more energy to heat up a metal or to heat up liquid water? Oh, gotta go back. We can see here that aluminum at 0.22, mercury at 0.033, and gold at 0.031 all take very little energy to heat up compared to liquid water. So the answer to this question, it takes more energy to heat up liquid water than it does a metal. This is why metals are good conductors of heat, because it does not take very much energy for them to get warm. So we are going to now introduce to you the calorimetry equation as Q equals ms delta T. Sometimes you'll see this equation written as Q equals mc delta T, whereas C is substituted for S. But regardless, it's the same equation, and we will define what each of these variables is now. Q represents the amount of heat energy, either in calories or joules. We will work with calories in this class. M is equal to the mass in grams. Delta T is equal to the change in temperature in degrees Celsius. And S is the specific heat. Specific heat has that weird unit of calories per gram per degree Celsius. This is my attempt at writing parentheses using a mouse, so my parentheses came out rather feeble. But we will use this equation to figure out either the amount of energy of a substance, the mass of the substance, the change in the temperature, or the specific heat. Every substance has a different capacity to absorb heat. This is what I showed you on a few slides back with the different heat capacities. And water has a very high specific heat compared to other substances. This is why it takes, in the spring, as winter is leaving and spring is coming on, it takes water a lot longer to heat up in the spring and the summer than the land does. The land will get much warmer much more quickly than the water, because the water has a very high specific heat capacity. Alright, at this point you should have a problem set to work through, converting calories and joules and kilocalories, and you will be using the Q equals ms delta T equation given specific heats to find either energy, mass, or change in temperature. So that's it for this video lecture. We'll see you in the classroom.